Ladies and gentlemen, not all heroes wear capes. Take this man for example.
Hello.
Now this is YouTube's Allegedly Dave, somebody I first became aware of when he embarked on an experiment into breatharianism. Now if you don't know what breatharianism is, it's where people lie to each other and tell them that they don't need to eat food to survive, they only need to eat food for pleasure. So let's see how his experiment went.
So, day one of the Great Breatharian Experiment. Surprisingly, for somebody who's done a 30-day fast and forgotten to eat for 8 or 9 days, I found the first day to be very difficult actually.
Yeah, but you did find it difficult, didn't you? How did you feel?
I felt hungry.
Shocking. Anyway, it appears that Allegedly Dave is back, and this time he's leading a team of flat earth masterminds to take on some Astrophysics PhD students in a debate about the shape of the earth. Now, we're going to review that debate and we're going to see the tactics that the flat earth team use to get around the fact that they've got literally no evidence for a flat earth whatsoever. So before we start, let's have a look at our virtual bingo card. And I wonder how many of these traditionally used flat earth arguments Allegedly Dave and his team will tick off today. Right, so let's take a look at what we've got, shall we? Number one, the old stupid argument that water cannot conform to the outside of a ball. That's always a reliable one. Number two, the ridiculous argument that gravity can't exist because Einstein and Newton disagreed on it. Number three, the equally stupid argument that we can't have an atmosphere next to space because gas always moves from a high pressure to a low pressure. Number four, ridiculous pictures that claim to show we can see too far so the Earth must be flat. Number five, the completely ridiculous argument that pilots don't have to periodically dip the nose of the plane to account for the curvature of the Earth. And number six, let's just see if they'll make up some completely random nonsense to try and explain some sort of phenomenon that is otherwise impossible to explain on a flat Earth. So the scene is set, so let's start the debate. What is our first question?
Question number one is, why doesn't the artificial horizon on a plane roll backwards during straight and level flight?
Yeah, I'll take this one, yeah.
So, over to you boys.
So straight away we can tick off our first tried, tested and debunked flat earth claim, and that is a claim that planes don't have to dip their nose as they go around the curve of the Earth. But unfortunately the astrophysicist being asked this question misinterprets it and seems to think he's being asked why do we not see or feel a curve when we're in a plane, which Allegedly Dave finds hilarious.
A straight line is actually going to be, on larger scales, curved, much like the Earth is curved on larger scales.
Yeah. That was the answer.
Yeah.
So Dave steps in to try and rephrase the question, but notice how this isn't a question about astrophysics or the shape of the Earth, it's a question about how the artificial horizon on an airplane works. And this is a really common flat Earth tactic, to ask you questions that are so far out of a normal person's field of knowledge that you can quite often get confused and trip up a little bit, leaving the flat earther feeling a little bit smug, even though they provided no evidence for a flat Earth whatsoever.
I think you're slightly misunderstanding the question. Imagine a plane before it takes off. Yeah, okay. It's got a gyroscope in the artificial horizon. Okay, it spins that gyroscope up to get the reference of the ground. Okay. Now, if that plane starts going over the curve of the horizon, yeah, the gyroscope will stay upright. It's rigid in space, so it will stay upright as the plane rounds the curve of the Earth. So the artificial horizon will roll backwards, yeah? But it doesn't. It stays straight and level. The plane is not going over a curve, but flying over a plane.
So I'm just going to explain that very quickly one more time, just for those people who aren't familiar with this argument. So let's summarise this point, shall we? We can take a plane, any plane, it doesn't have to be the plane the size of a planet like this one. That red arrow is pointing down towards the centre of the Earth, and the gyroscope when the plane takes off is in this orientation here where it's pointing to the top of the picture and the bottom of the picture, and that tells the artificial horizon that the plane is level. Now what Dave is saying is that as the plane goes around the curvature of the Earth, the orientation of the gyroscope will not change, but the orientation of the plane is going to change. So the relative orientations of the gyroscope and plane will change, which should cause an effect on the artificial horizon, saying that the plane isn't level anymore. Now, understandably, the astrophysicist here has no idea how an artificial horizon on a plane works. After all, why would he? It's not something your everyday person would look into. But he obviously knows that it's got something to do with gravity.
I don't see how it can be independent of gravity or anything like that if it relies on the horizon.
So let's help him out a little bit. Here's a short explanation of how the artificial horizon actually does account for the curvature of the Earth. Now, I have linked the full video to the animation you're about to see in the description below. It's only on for about 3 minutes and it's a brilliant explanation. Take it away. So welcome to the inside of the artificial horizon. These arrows here are pointing to the pendulous vanes, and that metal canister is what contains a gyroscope. Now these pendulous vanes, very much like a pendulum, are free to swing, and as such always point towards the centre of the Earth. As the plane goes over the curvature of the Earth, there will be a change in the relative position of the pendulous vanes and the canister. But as we can see here, that causes little slits or air holes to become exposed. But in the artificial horizon, when one air hole is more open, an air hole 180 degrees from that becomes more closed, and this causes an imbalance in the airflow coming out the air holes, which creates a force. And because this is a gyroscope, the effect of that force is seen at 90 degrees from the application of the force, causing the gyroscope to right itself and become level again. Now the frustrating thing for me is I've seen, allegedly Dave, debate artificial horizons many times, and I have seen over and over again people explain to him how pendulous vanes work, so I know he's well aware of it. So for him to still be using the artificial horizon as some sort of flat earth proof, to me is extremely dishonest. Anyway, let's look at question 2.
If everyone's okay, I'm going to move on to question 2. Yeah? If gravity is the only thing holding the air to the surface of the Earth against the tendency of a high pressure system to escape to a low or negative pressure, then when air is heated and so is less affected by a gravitational pull, shouldn't it then succumb to the force exerted towards a region of negative pressure? What?
Right, that was a pretty poorly worded question, but if you watch the entirety of this video, which I'll link in the description, it appears that what he's trying to ask is as the air above the ground, which is at higher pressure, starts to rise, because it's at a higher pressure, why does it then not just burst off into space? It is a pretty poor question, but it's answered with this little gem.
There's two competing forces. There's gravity pushing downwards, and then there's a thermal pressure of air pushing upwards. The laws of gravity dictate that the air pressure is going to be higher at the center, nearer the Earth than outside. So if you got a heated column of air that would rise away from the Earth, as it would rise, it will become less dense as it's less affected by the gravity as it will be at a greater distance, and thus have a lower thermal pressure pushing upwards. So that system stays in that equilibrium state, and that's called the hydrostatic equilibrium, and you can read a lot about it.
Okay. But that's a little bit too scientific for our team of flat earthers, and they want to avoid that at all costs. So they decided to take the conversation down a completely different route. Can you guess which one of our bingo points we're going to be ticking off now?
When you say thermal air pressure, what I'm seeing is you've got a vacuum next to a pressurized system, okay? And we always see, hang on, we always see when there's high pressure next to low pressure or zero pressure, a movement from between one and the other, okay?
Absolutely, they want to use a tired old lame argument that you can't have gas pressure next to a vacuum, so therefore the atmosphere can't exist next to the vacuum of space. Now nowhere in the heliocentric model do we have a high gas pressure existing next to a vacuum. Right up there, really, really high on the edge of space, the air pressure is practically zero because, as the astrophysicist reminds him, the atmosphere is a gradient.
It's a gradient.
But while that is sinking in, another member of the Flat Earth team decides to tick this little gem off our bingo card. Apparently he's figured out that the Coriolis effect is not due to the rotation of the Earth, but is caused by, well, let's see if you can figure it out, because it makes naff all sense to me.
I just want to make one point on this. I think what we're describing, when the sun rises, heats the air rises, and as you say, it's an equilibrium system, all the air rushes in. I think that's how we get the Coriolis effect. No need for a rotating globe to create it. It's exactly air pressure, air difference in temperature, difference in pressure, and the system kind of, being an equilibrium system.
And then comes one of my favourite parts of the debate, where it transpires that Iron Realm Media's own Adam Meakin is sat in the audience, and he wants to chip in by asking a question which is clearly plucked from Quantum Eraser.
For fuck's sake, man!
Yeah, that's him. Now, Quantum Eraser often says that when he Googles the term gas pressure, he finds Google definitions with the word container in it. So therefore, if we talk about pressure or gas pressure in our atmosphere, we are somehow admitting that the atmosphere must have a container. It's a ridiculously weak argument, and I'm actually appalled that Adam Meakin, who's a chemist by trade, is actually using this argument. But when he asks, he's instantly slapped down.
The scientific definition of air pressure is that measured within a container. What should it be?
Is it?
No.
Do you want to take it a second?
And then his question is answered with this rather elegant explanation.
If you imagine we take a random part of our ocean we're underneath, take a random bit of water, you make like a dotted circle and there's a bit of ocean there. That part of ocean, assuming there's no waves and assuming there's no motion, is staying in that one place. Now, you'd think gravity would make it want to go further down, but it doesn't, it stays where it is. That's because there's an inherent pressure taking place there due to all the water surrounding it. So because of that, you can imagine if we're using arrows like in basic mechanics, you've got an arrow going down and then you've got arrows in all other directions and an arrow going up. That's the up arrow is the pressure and that's what's balancing it, keeping it there. All these ideas can be explained with pressure and gravity in this way, and it does not require a container to do it.
Now, I'll admit that the next question asked by the flat earthers threw me off guard a little bit. It's just not one I've seen asked in a flat earth debate before. Let's see what it was.
How would you explain light slowing down and hitting a denser medium and speeding up after leaving that medium for a less dense medium when the law of conservation of energy prohibits such observations?
Now, the only reason I could think of that they're even asking this question is that they're trying to debunk our understanding of refraction, because if they can debunk our understanding of refraction, it makes it difficult for us to use refraction as the reason we see photographs like this, which of course is the famous Chicago skyline photograph, which relied on atmospheric refraction for us to be able to see that over the distance it was taken. But if you're still just a little bit confused about what the question actually was, let me use this picture to show you. What they're saying here is, as the light enters a glass block, it slows down, therefore it loses kinetic energy. And as it leaves, it speeds up again, gaining kinetic energy, thus breaking the law of conservation of energy. So let's see what the answer was.
There is a quantum mechanical explanation to this, but I don't think we have time to go into it. I don't have a whiteboard.
Well, I do. But let's let him finish answering his question first.
So the way that I picture it is that actually light travelling is essentially it hits an atom, that atom absorbs the photon, electrons within the atom are excited to a higher state, and then they drop back down and the photon is re-emitted.
So let's take a closer look here at what he was just saying. So the idea goes like this. The photon enters a glass and is absorbed by an electron, which is excited to the next energy level. When the electron drops down to its original energy level, it re-emits that energy as another photon. Now, the speed of the photons isn't actually changing here, but this constant process of being absorbed and then re-emitted makes it appear that the light is travelling slower through the glass. Now, that explanation would explain why the speed of light appears to slow down in the glass, even though the photons carry on travelling at the speed of light. However, there are some issues with it. And the biggest problem is this: when the electron falls back to its original energy level, the direction that photon gets emitted in is random. And so that will not allow us to have these consistent and predictable observations of refraction. Now, as the astrophysicist has already alluded to, there are quantum explanations for this problem. But in the description below, I've linked 2 interviews with 2 very, very high-level physics professors that go into this really, really deeply. I'd really urge that you go and check those interviews out. They're fascinating. All I'm going to do is give you the headlines and then hope you go and watch those. So at A-level, we teach Feynman's sum of paths answer to this problem. We would say that a photon travelling from here to here actually gets from here to here by taking a whole infinite number of paths, and all those paths will travel at the speed of light. But as they intermingle with each other, we'll get constructive and destructive interference, and what we'll find is that the constructive interference occurs along this line here, allowing us to see the light, and all those, the parts where all the other paths have interfered, we get destructive interference, and so we don't get to see the light. Now, that might sound a little bit fantastical, so a more classical explanation will be that the photon, which is really a disturbance in the electric field, is going to have an effect on the charged particles in the atom when it hits the glass. And those particles are going to give off their own electromagnetic waves, which are going to disturb the atoms next to those, which are then going to give off their own electromagnetic waves, which will disturb the atoms next to those, and so on and so on. So what we have through the glass is a huge number of different waves, all spreading out, and it doesn't look like that. Right, spreading out in all different directions, but again, interfering with each other, some constructively, some destructively, and the path that we see here is where the constructive interference has taken place. Now, those waves that are being given off and propagating through the glass are travelling at the speed of light, but the apparent constructive interference, the apparent ray caused by constructive interference, does move apparently slower. It's very difficult. Linked in the description. Anyway, let's have a look at the next question.
Can you calculate any planet's orbit based on gravity/mass alone when using all masses in the entire solar system and get a result matching the prediction algorithms of the proposed elliptical orbit of any planet? I couldn't say that backwards.
Right, so can we really use Newton's understanding of gravity to calculate the orbits of planets? Got it.
Short answer, yes, pretty much. We have a very good idea where all our planets are going in our solar system. We know where they're going to be, and we can continue to predict where they're going to be for the next 500, 600, 700 years. That's because it's based on really quite a simple system of just pulling in certain directions at certain velocities. We didn't actually discover Neptune and Pluto straight away, and yet they were predicted because we found that due to the way the planets are orbiting in our solar system, we would expect them to be there. And when we looked for them, we found them.
Of course, our understanding of gravity works so well that mathematician and astronomer Leverrier was able to take a good long look at Uranus.
No pun intended.
And he noticed that Uranus was wobbling.
No pun intended.
So at particular times and places, Uranus did have a wobble in its orbit, and Leverrier was able to use our understanding of gravity, thanks to Newton, to predict that there should be a planet behind Uranus causing this wobble, and not just to predict that there should be a planet behind it, but the exact location of it. And when he passed that data on to D'Arrest and Galley, and I know I've pronounced their names wrong, I always do, they were able to locate the exact position of this planet, and therefore Neptune was discovered. So I'd say our understanding of gravity works very, very well. I wonder what Dave and his team had to say about that.
I just wanted to make a little point, because this is the second time that you kind of waxed lyrically about Newton. Newton's theories didn't explain everything. Now, Newton wrote a huge tome basically to describe his theory of gravity. Now, when Einstein came along, he gave a completely different interpretation of what gravity is. So that means everything Newton produced was bullshit. No, bear with me, yeah? If you wrote all this calculus and came up with a theory that didn't quite match, what we observe, yeah, which means it had no relationship to reality, and Einstein came along and gave a completely different interpretation, which apparently does match up. That means that whole book is bullshit. He made it all up.
I actually totally agree with you.
What a surprise! We are now able to tick off the old tired argument that we don't know anything about gravity because Einstein and Newton didn't see 100% eye to eye. Amazing. Now, I know what you're thinking. You're thinking I deliberately cut that last clip short and I'm not going to show you the rest of it.
Yeah, Newton was wrong. Demonstrably wrong, in fact.
And yet it stood for 400 years.
Yes, but you can still apply his calculations to kind of most, certainly everything on Earth. Quite a lot of bodies in the solar system. His calculations work, well enough. Sure. He was wrong. This is why I say that nothing is ever fact. That things are just theories until someone comes along and proves them better. I'm sure, maybe in another century, 2 centuries, or whatever, someone might come along and say.
The world's flat.
Absolutely. Now, who was it who said that if they can see further, it is only because they are stood on the shoulders of the giants who come before them?
Hello.
No, Ranty, I don't think anyone thinks it was you. But anyway, the point is, in science, we take what works and we build on it and we improve it. And if something doesn't work, we disregard it, but we keep improving on what we know. What we don't do is take the flat earth approach, where we take everything we know, throw it out the window, and throw ourselves back thousands of years in time and have no clue about anything. Anyway, here comes the killer question.
So when Ligo, was it Lido?
Ligo,
sorry, yeah. When they first started doing their experiments, I wrote to ask a physicist, and I asked them a question, and they weren't able to answer. Well, they refused to answer. Okay. I've asked the same question over the years to various people. None of them answered me. Okay. So this might get a little technical, just a little bit. Right. So the way LIGO works is that it's a
No, I'll explain it very quickly, but if you want a really in-depth video on this, again, check out the link in the description. So essentially, 2 lasers are sent down the 2 different tubes or arms that you can see in this picture. When they return, they are totally out of phase, as shown in this picture. This means they destructively interfere with each other and no light is seen in the picture. However, a gravitational wave will slightly stretch one arm whilst contracting the other. This means that now the photons are travelling different distances, so they no longer arrive totally out of phase, and we can detect an intensity of light on the screen. So I wonder what Dave's problem is with this.
Right, so this is supposed to prove Einstein.
No, I think we have enough proof that Einstein existed. Crack on.
But what Einstein said is that it's not the gravitational wave isn't in space, it's in space-time. So if space contracts, then time slows down so that the speed of light stays the same. So if you're doing an experiment with the speed of light, you will never detect gravity waves, because if the gravitational wave, sorry, no. So that, yeah, if one leg shrinks slightly because of this gravitational wave, then time would slow down for that beam of light. So it will arrive exactly the same time as the other beam of light. No interference pattern. So if they detected something, that means Einstein was wrong. So if they don't detect something, that also means Einstein was wrong. So what do you got to say about that?
So this flat earth gravity debunking argument isn't one I've really heard before, but just like that question at the beginning of the video about the artificial horizon, it's not really a question that's offering any flat earth proof in any way, shape or form. What it is an attempt to show somebody up by showing them that they don't understand how a complicated piece of machinery works. So in simple terms, Dave is trying to say this. Dave is trying to say that as LIGO is measuring the distance of each arm, if a gravitational wave makes, for example, this arm contract, so the distance is smaller, then the time will slow down, meaning that we can't actually detect that change in distance because of the effect on time. All very complicated. Let's see what the astrophysicist said.
So,
leave it there.
Yeah.
Well, that's the best answer today.
This would absolutely be the case if you were doing this experiment with anything other than laser light, or light in general. Whatever speed you're travelling at, if you were travelling at half the speed of light and you fired a laser, you would see that laser go away from you at the speed of light. Yeah. So it doesn't actually matter about the fact that the light is slowing down because it's still travelling at the speed of light.
Don't try and blind us with bullshit.
So for somebody who doesn't know how a cutting-edge piece of technology like LIGO actually works, he gives a pretty good attempt at an answer. But Dave thinks he's got him on the ropes.
The point is, you're using well, Einstein says that it's not just space, it's space-time. You know, you change the space, time changes, so that the speed of light remains the same. That's the core of Einstein's relativity. Mm-hmm. So that means it can never detect a gravitational wave.
But the light is still travelling at the same speed.
Only because time is reciprocal to space. So it has to, according to Einstein, that's what has to happen. That's Einstein. It's Einstein. Don't argue with that. It's not me. It's Einstein.
It's not quite one over the other.
It is. That's it.
It is Einstein's theory. I'm afraid so. He's described it accurately.
Okay.
Go and read it, and we'll see you next year.
Now, this was the last question in the debate, and the Flat Earth team were able to leave feeling a little bit smug that they'd exposed the fact that the astrophysicists didn't know how the inside of an artificial horizon on a plane worked, and they didn't understand how the cutting-edge technology at LIGO worked, which is a little bit of a cheap shot, considering that they offered literally no proof of a flat earth whatsoever throughout the entire debate. Anyway, this last question about LIGO did trigger me into doing a little bit of research, and I found that it was actually quite complicated. For example, one website I visited summed it up like this, just for simplicity. Yeah, very simple, isn't it, Dave? Do you think you can explain that to me? And again, you know, just for simplicity, this guy here tells us that the time dilation is actually linked more to gravitational potential and not the stretching of space-time, and there is not a linear relationship between the change in gravitational potential and the change in space-time. Which means that there's not a linear relationship between the change in distance and the change in time, so we can measure the change in distance. Now, I have no idea if that's right or wrong. It's really high-level stuff. Do you know, Dave? Now, I sometimes doubt if Dave is capable of tying his own shoelaces, let alone explaining the complexities of time dilation. But I need a proper physicist.
Conspiracy cats.
A proper professional research physicist.
Conspiracy cats.
Yeah, a research physicist who actually has friends who work at Ligo.
Conspiracy cats.
Of course, AB Science. Now, for those of you who don't know, AB Science is everything I've just said and more. He's going to contact his friends at Ligo and produce a video specifically around this question. However, he has already given me the simplistic version of the answer, if one exists. So has a new friend of mine called Atheo, who's been a massive, massive help to me over email over the past couple of weeks. So thank you very, very much, Atheo, for your help. Now, both Atheo and AB Science basically tell me that yes, as the gravitational wave is stretching or contracting the arm of LIGO, the light travelling through that section is going to experience that time dilation. However, to an outside observer, we are not going to experience that time dilation, so therefore we can detect the change in length that the light has got to travel. But like I said, watch AB's channel, please subscribe to it, and you'll see a much more detailed and very, very high level, I'm sure, video coming your way soon. So to summarise, again, we've seen another flat earth debate where, surprisingly, we haven't been told that water can't conform to the outside of a ball. But unsurprisingly, we are yet again offered literally no evidence of a flat earth. Only more attempts to trip up the person they're debating with by trying to ask them how complex machinery works. Anyway, I'm off. Bye.